Alright, hello everyone, and welcome to another IFT 372 online study session. Apologies for not being able to make it on Thursday, but I figured that we'll add a little bit more time today, and hopefully we'll be able to answer all the questions that everyone has. Let's see. I've got a couple questions from people just contacting me individually about the midterms. They had some questions about some problems with rounding and numbers, and again, Dr. Helm does review the midterm answers for things like rounding error. And so if you have a number where you put in an answer but you got a slightly different answer than what it was looking for but you think is still right, those should be reviewed over the next few days. But do keep an eye on that sort of thing. If there's a couple questions you think you got right but was marked wrong because it automatically marked or it didn't exactly match what was typed in, keep an eye on those, and if they're not fixed by in a week or so, get back to either myself or Dr. Helm or the grader and make sure those corrections are made. Because again, it is, especially with the fill in the blank or like type in your own answers, there are plenty of ways that you can type in an answer that we didn't expect, and that can cause it to be marked wrong when it's really not. But as normal, we'll probably give it a couple minutes here just to let people show up, and then we can get going with either the homework or the activity. And then if we have time later, after we cover the immediate stuff, we can go over the midterm and take a look at if anybody has any questions about particular problems. Okay, so we've given it a few minutes to wait. We'll get started, and then we will, if people show up late, we can address it when they show up. So Steven starts out by asking, he doesn't know the equation for the short dipole antenna, so he can't figure out the problem, and there's a couple of them that are related to short dipole antennas. Yeah, so let me see where that formula is given. Let's see. Because it is a distinct formula, and again, yeah, it can be, if you don't know what that formula is, it can be tricky to solve those problems. So let's see. be under week 4 if it's not in week 5. Okay, so let me move this message now that we've got this. So the key word when you're looking at that is that it's saying that we're dealing with a short dipole antenna, and if you look, I don't have it on the screen for you to see, but in week 4, lecture 6-1, which is the Antenna Basics Part 1, it gives us a slide that covers the short antenna application, which is basically what we're talking about here, because on the slide it tells us that the practical elementary dipole is a center-fed antenna having a length that's very short in wavelength. And so that's basically what we're talking about. We're talking about a short elementary dipole. And so given that formula, or given that case, given we have an antenna that fits that criteria, we have a formula of radiation resistance equals 200 L over wavelength, or lambda, quantity squared. Let me just be clear that that's an L. And so again, this is for short dipole antennas. We have a formula that says our radiation resistance is equal to 200 times length over wavelength squared. And that's available in the week 4 Antenna Basics, lecture 6-1, part 1. And so then at that point, we can start plugging in our numbers. So, for example, for that particular problem you gave, let me just bring it up here so that we can see it. When it's asking what is the radiation resistance, so we're solving for our radiation for a short dipole antenna, 118.5 millimeters long, which is our length. If the uniform RMS current is 300 milliamps and the frequency is 1900 megahertz. Now again, looking at this equation, we don't care what the RMS current is. That doesn't affect our radiation resistance. The amount of current we're pushing doesn't affect the radiation resistance. All we care about are the frequency, or we care about the wavelength, but we can find it with the frequency and the length of the dipole itself. And so if we go to plug in the numbers here, we have R equals 200 times, and remember that with length we want to basically bring it down to just the base unit. We want to bring it to meters, so we have 118.5 times 10 to the negative third, and then we divide that by our I guess we should do our frequency conversion first. So again, remember, we're given a frequency, we need to find the wavelength. So we have wavelength equals C over F. And then at that point, we just do some substitution in, because we know our speed of light's the constant. So C divided by our frequency, which was 1900 megahertz. And eventually that gives us a wavelength of 157.9 millimeters, or 10 to the negative third. And so back over here, we'll add that number back in. And then that whole quantity that we just covered there is squared. And so given that, we can plug back our numbers and we end up with, let me do the math here on the calculator. We have 118.5 times 10 to the negative third divided by 157.9 times 10 to the negative third, quantity squared, times 200. And that gives us a radiation resistance of 112.6 ohm. And so again, we don't care about the current at all because the amount of power we're pushing through doesn't affect our radiation resistance at all. We would only care about current if we were asking to find the power involved in the formula. Or if the question was asking us to find the power, then we would care about current because that makes a difference. But for radiation resistance, it doesn't. Yeah, and like you said, if you were just missing that first part, you were just missing the first equation. So I'm sure the rest of it comes together once you have that first piece. But that first piece is a important one. And so again, just to be clear for anybody who's coming in after the fact, that was additional question 5 from the week 5 homework. Alright, so again, we're just waiting for anybody else to join in or ask questions. Okay, Stephen has another problem that was a little tricky, so let's see what he's got. Alright, 6.15. Suppose a car is moving through a suburban environment that has a wireless channel with a coherence time of 10 milliseconds and a coherence bandwidth of 600 kilohertz. Okay, I know which problem you're talking about. Alright, so the big thing here, let me see if I can pull up the example. So the thing about this question is it's basically asking you to tell what sort of fading is occurring in this particular environment. So let me bring up the original question. Let's see, where's the original question? Okay, so the one part of information that you didn't include there. Alright. So again, this is question 6.15. And we're being told that suppose a car is moving through a suburban environment that has a wireless channel with a coherence time of 10 milliseconds. So we have time coherence equals 10 milliseconds. The next point is that we have a coherence bandwidth of 600 kilohertz. So bandwidth coherence equals 600 kilohertz. And then finally, we know the bit rate of the signal is 50 kilobits per second. 50 kilobits per second. And we're being asked to characterize the channel as either is the channel fast or slow fading. And then also, are we looking at flat or frequency selective fading? So those are the questions we're being asked, and these are the variables that we're given to solve it with. And so if we look in the book, and this might be covered in the lecture materials as well, but I'm looking at the book since I have it in front of me. On page 109, we're told that a channel's coherence time is the time over which channel stays relatively constant, and so this is what's basically we're being used for looking at our fading. And so what we're looking at is our channel, again looking at 109, it's important to note the coherence time basically has a significant effect on the signal, and this is straight from page 109, depending on the bit rate of the signal. And so the book says that a signal has a bit time, so time bit, equal to 1 divided by our bit rate, or our rate of bits. And so in this case, if we look at the equation, we see that we're given a bit rate of 50, or 50,000 technically, right, because it's 50 kilobits. And so 1 divided by 50,000. And again, if we plug this number in, we end up with 2 times 10 to the negative 5th. And so now, this is what we're looking at for basically our bit time. And if we go back to page 109, it states that if our coherence time is, is much longer than our bit time, then the channel is slow fading. And so given these two pieces of information, the bit time that we just calculated versus the coherence time, if our T coherence is much greater than our T bit, then the channel is slow fading. And so the question here is, how much greater is much greater? What's our threshold here? And generally we can use 10 times greater as the value that we're making the comparison to. So does that mean what we're looking for here is if our T coherence time, our 10 milliseconds, is greater than our T bit time by a factor of 10. And so if we compare our two numbers here, we have 10 milliseconds compared with 2 times 10 to the negative 5th. So let's get rid of our 10 milliseconds. Let's just make it back to our base unit. So we have, instead of saying 10 milliseconds, we can say 0.00 or 0.010 rather. Compared to, and again, if we do 2 times 10 to the negative 5th, we have 0.1234. Because again, we count out the spaces, 1, 2, 3, 4, 5. And so right now, it looks like our coherence time is indeed more than 10 times larger than our bit time. Which means that this channel is slow fading. And again, we know it's slow fading because our coherence time, which was given, is 10 times or more our bit time. And again, if you're asking what the bit time is or why we have to calculate it, look at the equation. We're using 1 divided by the bit rate. And so that's telling us the amount of time it takes to basically transmit the single bit, right? Because if we're transmitting 50,000 bits in a second, it takes 2 times 10 to the negative 5th seconds to transmit a single bit. And so our coherence time is much larger than the time it takes to send a single bit. And so we can send these bits without having too much trouble, and that's basically what the coherence time is telling. Because again, on 109, on page 109 in the book, the coherence time is the time that the channel stays relatively constant. So if we can get a large number of bits sent while the channel is relatively constant, it's not going to fade very quickly, because the conditions are staying the same for a significant amount of time, longer than we need to send a single bit. Steven's saying, that's why I didn't understand what is RS. So that might be the spreading, which we're going to probably look at in a second here. Okay, yeah, so again, this is just for part A. This is addressing if we're looking at a fast or slow fading channel. If we then need to look at the flat or frequency selective, this is the next step. So if we go still on page 109, and if we look at the next paragraph, so we've already addressed coherence time, and page 109 says the other small scale effect, multipath fading, can cause distortion and intersymbol interference. Flat fading is the type of fading that occurs in all frequency components in the same proportion simultaneously. And so what we're looking at here, it's fairly similar, is we're looking at a coherence bandwidth. And signal bandwidth. And so what we're looking at here, again, it's fairly similar to what we just handled. Where are we here? Oh, I see what, yeah, I see what the confusion's coming from here. So basically, let me double check my numbers to make sure we're right here. Let me double check something, because I think RS is just a case of using different vocabulary, if you will. But I need to test the numbers to make sure. So basically, Stephen, let me just catch up with what he said here. So TC would be this. (600 kilohertz). Okay, Steven, so I agree with you here, but then can you explain where these numbers are coming from? Just really quick. I agree with your thinking. No, I think you are correct. So in the case, if you're reading the same page I am, which again, it took me a second to look over, when they're using the term, and again, this example is on page 111, which basically gives you their examples of their numbers to look over. But they're saying that assume that our bandwidth of the signal is approximately equal to the bit rate of the signal, which they use RS for the rate of the signal, but either way, that's their approximation. And so for our problem here with our bit rate of 50 kilobits per second, we're going to assume that BS is equal to 50 kilobits per second. Oops, there we go. And now for our test, again, we have to check that our coherence bandwidth is either 10 times greater than or equal to, or not 10 times greater than or equal to. And so if we look at our numbers here, we have a coherence bandwidth of 600 kilohertz, and we need to see how it compares to 10 times, because again, this is what we're looking at. We're looking at 10 times. Is it greater than or equal to 10 times our bit rate, which is 50 kilobits per second? And so if we do that comparison, we have 600 kilohertz compared to 500 kilobits per second. Or technically this is at this point kilohertz now. And doing that comparison, we see that it is greater, or significantly greater. Which means, because it's significantly greater, we're experiencing flat fading in this channel. And again, we know it's flat fading, or it makes sense that it's flat fading, because yeah, and so Steven's giving his explanation as well, that the coherence bandwidth, that should be BC, but yes, is 600 kilohertz, and then the bit rate is 50 kilobits, which is roughly equivalent to 50 kilohertz. And so again, it makes sense that this is flat fading, because if we're looking at the bandwidth over which the signal remains relatively constant, if we're not using that much bandwidth, if we're staying within that relatively constant bandwidth, then our signal should be relatively constant too. We shouldn't experience changes in strength or weakness of particular frequencies if we're in a relatively constant bandwidth channel. If we're staying in there, then any change to the signal should happen to the whole thing. And so we have flat fading, not frequency selective fading. And again, this example is illustrated on page 111. Basically 109 to 111 is the section in the book that discusses this. And so if some of this is not making sense, or you're not seeing why we have to check for this relationship of much greater than, then I would definitely review those sections, because which example is it? Example 5.5 on page 110 basically works this problem out with different numbers, but the concept's the same. Let's see. So Ryan's just joined us, and he's asking if anybody's asked any questions relating to question 4. Yes, Ryan, we did cover that. We covered question 5, technically. Was it 5? Yeah, we covered question 5, but let me just really quick go back over and show you the formula that we used for that one, because I think once you have the formula or the equation, then you can go from that point forward. So again, the formula for this question, radiation, there we go, for a short dipole antenna is 200 times length divided by wavelength quantity squared. And so that's what we're looking at for the short dipole antenna radiation resistance. And that's available in week 4. Let me make sure I have that. Week 4, lecture 6-1, part 1, the short antenna basics, part 1, or antenna basics, part 1, sorry. Slide 12, which is talking about the short antenna application. Let me just write that down. Lecture 6-1, week 4, 12. And so once you have that formula, I think going forward and plugging in the numbers aren't too tricky. Just make sure that, for example, when you're using the length, you want length to be in the base unit of meters. You don't have to do that, but I think it's helpful just to keep everything consistent. Otherwise, you have to make some other changes that can become more complicated than it needs to be. And Ryan's clarifying, so we do 300 equals 200 times length in meters divided by wavelength squared. Yeah, you're absolutely correct, except we're given the frequency. Hold on. Yeah, and so you're solving for, yeah, exactly, yeah, you've got it. And so you can solve it for the wavelength, and then you can solve it for the frequency based on the wavelength, yeah. 9 gigahertz. So Steven's saying he's getting 9 gigahertz. That's a little high. So let's see if we can work through the problem here. Just make sure. I suppose I should leave that up. So we have our formula here. We have 300 because we're given the resistance in ohms equals 200 times 217.6 times 10 to the negative third divided by, and there's two ways to really do this. We'll just start with wavelength. And then that quantity is squared. And so we'll divide out the 200. Equals 277.6 times 10 to the third divided by squared. I'll just check in with the chat, okay? So now we need to take the square roots. So 217.6 times 10 to the negative third divided by 1.2247. And then just plugging these numbers in. Okay, so with this I got a wavelength equal to 0.177676. And so then we have our usual equation is wavelength equals C over F. So of course we'll need to rotate things around. So we get frequency equals C divided by wavelength. And so frequency equals 3.0 times 10 to the 8th divided by 0.177676. And that gives me a frequency of 1.688. 1, 2, 3, 1, 2, 3 gigahertz. And so that's the number I get just plugging through the numbers. So you may be able to spot a math mistake you made in there. If not, if any of that seems unclear, I can go back over and explain how what I did where, because I kind of rushed through that one just to get the math down on paper. Yep, wrong value for C. Yep, that'll do it. Make sure I have the right value for C, but that would explain different math number, different number. And so again, this is based on the original short dipole antenna formula, which is R radiation equals 200 times length over wavelength squared, quantity squared. But we have to solve in a different order because we're asked for a frequency, and so we have to solve for our wavelength, and then we can convert wavelength to frequency based on the wavelength equals C over F relationship. Ashley requests number 7. Sure, we can look at number 7. Alright. So, for number 7, let's look at the numbers that we're given here. So this is additional 7. All right. All right. So we're asked for the power level entering the first active stage of the receiver at 1900 megahertz, being fed by 25 meter coax. Okay. So we're looking at power level at first active stage. So in other words, we're looking for the RSL. And we know our frequency is 1900 megahertz. We have 25 meter coax with a loss of 20 dB per kilometer. Okay, so that's transmission line loss. And we know our IRL is equal to negative 134 dBW, and our receiving antenna has a 1 meter dish. So this question's essentially asking you to work with a parabolic antenna. Ashley asks if it's like number 18 from the practice midterm. Yes, it has some of those same elements, but it's slightly different because we're also talking about a parabolic antenna. And so the formula is basically the same. We have RSL equals IRL plus our antenna gain minus transmission line loss. And so this is similar to the practice question 18 because we have transmission line loss. I don't need this much space. I might have to work over it. So our line loss, we've covered that it's 20 dBs per kilometer of cable, but we're only using 25 meters. So this is similar to practice 18 because we have defined the actual amount of loss that we experience. And so again, if we have 20 dBs per kilometer, so we basically have 20 dBs per 1,000 meters, and that tells us that we have a line loss that means that for every meter, we lose 0.02 dBs per meter. And we have 25 meters, so line loss equals 0.5 dBs. And so over 25 meters of coax, our transmission line loss is 0.5 dBs. And that's like the practice midterm problem. And so we can plug that number in over here. Minus 0.5. And then again, we also happen to know the IRL because it was given to us. So RSL equals -134 plus antenna gain minus 0.5. And so the problem here now is that we don't know the antenna gain. We need to figure out what our antenna gain is, dB. And the important information that we're given regarding this is that our receiving antenna has a 1 meter dish and we assume that it's 55% efficient. Oops, there we go. And so over here, does anybody have off a formula sheet or their notes the formula that we need to use to calculate the gain of a parabolic antenna? If not, I can pull it up for you, but let's see if anybody has it in front of them. So Ryan has 10 log 4 pi times area of aperture times aperture efficiency divided by wavelength squared. And then Ashley has an alternative one, which is 10 log 4 pi a area times efficiency. Okay, those are actually the same formula. So yeah, so that's one of the formulas we can use. There's also a shortcut, but we can deal with those formulas since you both gave me the same ones. So we'll start with that. 4 pi a, and then Ashley's got the nice efficiency symbol. Divided by wavelength. Squared. Alright, so that's our formula. And so we have 4 times 3.145, and again, etc. pi. We'll just put pi in there so you can use your calculator for that one. And then we have the area. And then, so I'm just plugging in some numbers here to make sure we're on the same page. And then I'll come back and make sure everything's going well. Let me make sure I'm doing this correctly. So it's 4 pi times Let me see. I used a different formula for this, so I'm just double checking to make sure that answer should be equivalent, but I'm not getting the same number when I plug it in, so let me double check. And again, just for Ryan, who joined late, we're here for another hour because we missed Thursday. If you need it, if we want to. Okay, so Ryan's posted the equation that I actually used, which is much easier, but you should be able to do it with the other one. I'm just trying to figure out why my numbers aren't adding up. So for now, for the sake of argument, let's use Ryan's easier formula, but then I do want to go back and see why I wasn't getting the right number with the original formula that was posted. And so let's tackle the easy formula just so we can get an answer out, and then I'll go over and double check my math and see why the first answer was not working out the way it should. So Ryan's the shortcut formula is gain equals 20 log diameter in meters plus 20 log frequency. And again, this is just the formula that I used the first time, so I'm more familiar with it. But you should be able to do it with the other antenna gain formula as well, which was originally posted. I just need to figure out why my math was off on that one. And so we'll just do this one for now to get an answer written down. But then we'll go back over and figure out why the other answer was not working out. At least for me. It's possible that other people had it working well. And so this is basically the shortcut formula for when you have parabolic gain and a frequency. It's important to note that this frequency has to be in gigahertz and that has to be in meters. So in this formula, Ryan, it actually frequency has to be in gigahertz if we're using the constant of 17.8. So you're right that we need to convert 1900 megahertz, but we have to convert it the other way. And so when we plug in these numbers, we have, and again, right here, this is asking for the diameter of the dish in meters, and we're originally told that it has a 1 meter, let me make sure. It's a 1 meter radius dish is originally what we're told. So again, if it's a 1 meter radius, then the diameter has to be 2 because it's twice the radius. And then 1900 megahertz is the same as 1.9 gigahertz plus 17.8. And so that's a tricky part that you'll sometimes get caught over, is that you don't realize that that's asking for a diameter and you're given the radius instead. And yeah, that's not distance, it's diameter. So again, plenty of places for you to potentially make a mistake there. And if we plug in these numbers, we get 6.02 plus 5.575, 58, 17.8. And that ends up with gain equals 29.4 dB. And so Ashley got 31.91. Were you using Ryan's formula or were you using your formula? because that's potentially in the realm of rounding distance or rounding error. Okay, rounding. Yeah, as long as you can show your work and that you use the generally correct formula, rounding problems should be okay. Yeah, Ryan got 29.39. And that's using Ryan's. Okay, so yeah, everybody used... I think Ryan's, the shortcut formula is the best one to use there. Like I said, you should be able to use the original parabolic antenna gain formula. Even though it's a little bit longer, you should be able to use that. But when I was just testing it now, I wasn't getting the right numbers. So I have to go back and verify why I was getting a different number on that. But that's what we're looking for here, is that we have our gain there. And so again, that is solving for the antenna gain. And so we can go back to our actual formula for this problem. RSL equals negative 134 plus 29.4 minus 0.5. And that gives us a final RSL equal to negative 105.1 dBW. And then again, this is in dBW because we started in dBW with our IRL, but you could write dBm or 2 if you wanted to or wanted to practice. That's our final answer, is negative 105.1 dBW. And I'd encourage anybody else also to try using the other formula, because again, it should work. I don't see a reason why it shouldn't work, but I was not getting the same number. But this is the method I used, and this is what I think the easiest way to get what you want, as long as you know that other formula. And again, as long as you can show your work and that you use the correct formula and work through it, rounding is generally fine. I'd always encourage you to leave as much rounding until the end as possible, but generally you shouldn't get marked down if you followed the proper steps and just had some slightly different numbers. So Steven's asking 6.7 part A. Let's take a look. Okay, so this is problem 6.7. And part A is asking, so the entire question, instead of assuming a free space environment in problem 6.6, assume an urban area cellular radio scenario. Use a path loss exponent of n equals 3.1 and a transmitter power of 50 watts. What is the range of path loss exponents for this environment? Okay. So generally this is pretty much straight out of the reading. It's asking you for the range of path loss exponents for an urban area cellular radio scenario. So if we look believe there is a table that contains all the numbers you would need. Let me see if I can find it. At least we know it's in chapter 6. I just have to track it down. Or I would assume it's in chapter 6. Let's see. Okay, so if you look at table 6.5 on page 175 of the book, it gives us a table of path loss exponents for different environments. And again, this question is asking you, assume that we're in an urban area cellular radio environment. And in that table, the path loss exponent is listed as anywhere from 2.7 to 3.5. So that would be the range that you're looking for question 6.7, part A. The range, and based on table 6.5 for urban area cellular radio environment, you have a path loss exponent from 2.7 to 3.5. So I'll write that down here since we're done with question 7. Steven says he thought it was asking for something more intense. Nope. It was just asking if you were going to start doing math problems in this situation, what would you be using for the path loss exponent? And so they tell you to, in the actual text of the problem, they tell you to use a path loss exponent of 3.1. And that fits within that range. So it's basically asking you what would be the possible numbers you could use for this situation. And that table tells us that it's anywhere between 2.7 and 3.5. And they tell us we're using 3.1 for this particular scenario. And so that's the extent of what part A is asking you, is just what numbers could you have used if we didn't tell you for this specific case it was 3.1. And then Steven says part B is throwing those numbers in with n as 3.1 instead of free space path loss. And yeah, that's correct. So we're not assuming a free space loss environment. We're instead assuming that we're in an urban area cellular radio environment, which has a path loss exponent of 3.1. And so we plug in those numbers into, where's our formula here? And we're given certain numbers again. We're given the frequency, except like you said, we are not in the free space environment anymore. 175. So again, for part B, we're looking at the general path loss. Or I guess path loss formula, which is 20 or loss dB equals 20 log wavelength 10n, and n is our path loss exponent, log d minus 10 log ATAR. And again, that's the antenna gain of the transmitting, antenna gain of the receiving. Or if we want the frequency instead of the wavelength, we can do that too. Those are the two variations based on whether you want to use the wavelength or your frequency in your calculation. Either one works, you just have to use a different formula. And so when we plug in these numbers, alright, let me see here. Yeah, Ryan just says he needs to leave. No worries. Like I said, we're going to keep going for another half hour or so, but it will be available later. Alright, Steven says, I ended up with 20 log 900 times 10 to the 6th plus 20 log. Yeah, Steven, that looks absolutely correct to me. He beat me to it a bit. I was having some math issues. So again, Steven's using the frequency form of the formula. And yeah, he fixed, yeah. That was the only issue I saw with that, but otherwise I think your answer was right. And so he's using the frequency loss formula because that's what we're given. Or, sorry, Stephen, can you just clarify the initial formula you used? Because I think I see what you're using. But I just want to make sure we're on the same page. Okay, so there's Stephen's initial starting formula with 20 log f plus 10n log d minus 147.56. And which page, or where did that original formula come from? Because that's different than our formulas here, and I want to make sure people understand which formula they have to use when, because that seems to be a sticking point for a lot of people. So I want to make sure we get why it's different. To be honest, I found that in the book. Yep, sure. That's entirely fine. So what that is basically is let me make sure. I'm just looking at this and I want to make sure that I'm doing this correctly, or if I made a mistake with using the first bit. 20 log 900. Because I might have made it too confusing by showing the general formula that we don't actually need for this problem. So let me make sure. Okay, so here's the thing, is that the free space, what Stephen gave in, Stephen's formula is correct. It's the correct one to use. But most of you are probably familiar with seeing it like this and realizing that it's the free space loss formula. This is the formula that we use when we're assuming that it's a free space loss environment and we're just looking at the loss that we experience over the free space. But really, we're used to using this formula for free space loss, which again, we want to do because the question's telling us that we're in a free space loss environment. But, hang on, just jumping to the right part of the book. The reason that this is our free space loss environment is that the actual formula is 10 times n log d. And so for free space, our n is free space n is equal to 2, but we've already been told that we're using n equals for urban area cellular radio, n equals 3.1 for this problem. So instead of doing our normal free space loss formula, which is 20 log d, we're instead using 20 log f plus 331 log d minus 147.56. And so that's our distinction that we're using for this problem, is that we've been told that our path loss formula is different. But that's the only change we have to make. We're still using the same path loss formula, except we're not using the free space exponent anymore. We're not using n equals 2. We're using n equals 3.1. So if we do the math here and plug in the numbers, we get 93.52 as our loss. And then we need to find the received power in dBm. And that's basically what we just, that's basically the problem. But the core part is why we have to use this different number here in this formula. And then, like Steven says, we have 47 dBm, and we subtract out the path loss that we just had. And just to clarify, Steven, where's that 47 dBm coming from? Because we just found the path loss. We found the 93.52. But how did we find the original power that we're subtracting from? Steven says from the 50 power for transmission. That's correct. So we're told that the transmitting antenna is using 50 watts of power. It's transmitting 50 watts of power. And if we convert that to dBm, or dBW, sorry, we end up with 16 and change, 16.9897 dBW. And so that means we're transmitting with almost 17 dBWs. And if we want dBm instead, we just have to add 30 dBs equals 47 dBm. And so we're transmitting with an original power of 47 dBm. We lose 93.52 dBs of power over the channel. And so that means when we're receiving the power, our received power equals 47 minus 93.52. And that means our final answer, our power received, equals negative 46.52 dBm. And so again, most of that is familiar after we look at the path loss formula bit, because that's what's important. We're so used to doing 20 log frequency plus 20 log D minus 147.56 for free space, but because we're using a different exponent, we're using n equals 3.1 instead of 2, it's no longer 20 log D, it's now 31 log D. But that's the only distinction we have to make, is that we're changing that exponent out, but then otherwise the formula is the same. And then part C is to repeat with a bigger distance, and then part D is to repeat but assume that your antenna gain is 2, or that you have an antenna gain of 2. But both of those are fairly handleable now that you've done it once. I guess really quick we'll talk about part D, because part C is just repeating what we just did with a distance of 10 kilometers instead. But for part D, it's saying that we have to assume that, let's see, 6.7 D. It says that assume receiving antenna has a gain. Assume gain receiving equals 2. And so how does that affect our final answer? If we know that the receiving antenna has a gain of 2, and that's just 2, that's not 2 dB, that's just 2, what effect does that have on our final received power? I just want to make sure everybody gets this part, and then we'll move on. But again, part C is just repeating the same math with a different distance, but part D is asking something a little different. So how does a gain of 2, just 2, affect our final power? Stephen asks if that'll change N. It won't change N because we're still going over a cellular environment. So that's not where it has the effect. Remember our general architecture. Let me clear some of this up. Remember the general architecture formula, which is RSL equals IRL plus receiving antenna gain minus transmission line loss. And so if all we're changing is the gain, the IRL stays the same. We don't really care about transmission line loss because we'll assume there is none. And so all that's really changing, and so Stevens changed his mind. He said, oh, perhaps we need to add 2 dB to our final value. It's not 2 dB, but you're close. And so remember that this formula is all in dB. And so if we have a gain of 0.2, and we need to add it into the formula here in dB, the IRL stays the same because that's not changing this problem. And so, but yes, and so there Stephen says if our antenna gain is just 0.2, which it is because it's not told that it's in dB, we have to add in 3 dB to our final answer. Because if we're increasing the gain if we're doubling the power, which is what a gain of 2 does, we have to increase the power by 3 dBs. And so that's all you'll have to do for part D, is once you've done part C, you then have to add 3 dBs into your answer because we've added an antenna gain of 2. And so that's what I wanted to go over and double check because I figured that might catch some people off guard. And so let me write that in. So 10 log of 2 equals 3 dB, just about. And that's generally the rule of thumb we can use. When you double the power, you add 3 dBs to your decibel value. And so that's what we need to remember for that, is that it's just a gain of decimal 2, but when we add to power, if it's in dB, we have to add 3 dBs of power. Or 3 dBs. dBs aren't a power unit, but you get the point. We probably have time for about one more question. If we have a specific homework question, or if we want to look at the midterm, we can do that too. I'm open to pretty much whatever we want to talk about now. We are coming up on the second hour, so this marathon session is wrapping up, but we have time for a couple more questions. And again, I apologize for not being able to make Thursday, but hopefully this has made up for it and let you address some of your questions. It's hard to say what's better, a Thursday or a Sunday, because Sunday you've had time to work on your own and you probably have more questions. But Thursday you have time to do it too, so. Next week it should be back to normal. There will be a study session at the regular time on Thursday. As far as I know, that'll still work. And then next Sunday as well. So we should be back to our regular schedule next week. Does anyone have any other questions? Just checking in. All right, well let's go, Stephen. Again, I'm not going to cut exactly off at an hour, so at noon. So if something does come up, we'll have time to address it. I'm not too worried about that. So if you have questions, let's do it. .1 was a little confusing. Let's take a look. Where's 8.1? Okay, yeah. All right. So what did you have generally for this question? It's basically asking you for just a general sort of description of them. You don't have to go into too much detail. What did you have? I guess we can start with what you had for OFDM. Figured out the space 15 kilohertz. Okay, that's probably, just to give you an idea, that's probably a little, you don't need to get that specific for this problem. You're welcome to, but you don't need to get that specific. It's really just looking for a general kind of description, a very general description about how OFDM works. So it's like, what sets OFDM apart for something like QPSK, for example? So what sets OFDM apart from other modulation schemes or multiplexing schemes? I guess the main thing that it's really looking for is for you to understand that we have to do problem 8.1. Oh, problem 8.1. Hold on. Oh yeah, look at that. I'm sorry, I didn't see the sheet I was looking at did not have problem 8.1 on it. Let me take a look at that. Sorry, I misunderstood what you were saying because my sheet was different. I thought you were talking about question 8.1. Let's see. Let's see, problem 8.1. Alright, give me 1 second to get back on the right page now that I know what you're talking about. Alright, 8.1, let's take a look. Okay, so like you said, for an 18 megabits per second LTE data stream with a symbol time of 66.67 picoseconds, how many subcarriers are created? Okay. So if we go back and look at let's see. It'll take me 1 second to look this up because I haven't considered this problem in a while. So Stephen, you originally said you figured out their space 15 kilohertz apart. Okay. So let's take a look. The big information that we're looking at for this problem is we have a symbol time and we have a bit rate. We have 18 megabits per second. We know it's LTE, and we have a symbol time of 66.67 picoseconds. And so if those are the big variables that we need. So now we just have to find something that puts all those together. So let me see. And so like you said, each subcarrier is about 15 kilohertz. 1 second. network is freezing up. Sorry about this. Okay, here we go. So again, we know that the key information that we're looking at here is that we have a symbol time of, given in the problem, 8.1. .67 picoseconds, I think it is, but let me pull it up here so I can double check. Yeah, okay, so our symbol time equals 66.67 picoseconds. (10 to the negative 6). And so that time is basically saying how long an individual symbol lasts. So that's the amount of time that one individual symbol takes up in transmission. And so if that's how long one individual symbol takes, we can figure out how many symbols there are per second. And we do that by saying 1 second divided by 66.67 times 10 to the negative 6 equals number of symbols per second. Because remember, each symbol takes 66.67 times 10 to the negative 6 picoseconds. So we need to figure out how many symbols fit into a single second. So by doing this math, we end up with about 15,000. And again, that's with some rounding error, but we'll just round up to 15,000. But remember, since we're using OFDMA, because it's LTE, or we're using OFDM rather, OFDM or OFDMA, that's per subcarrier. So we have 15,000 symbols per second, and that means we have 15,000 bits per second per subcarrier. Right? Are we up to that point? Let me just go back and explain why we have, because I think somebody's going to have a question why that's the case, what we just did there. Okay. So Stephen, if you're following along, so you get the relationship between why 15,000 symbols per second is 15,000 bits per second per subcarrier. Because that's the only part that I think might be a little confusing at this point. And I want to make sure that's clear before we move forward. So if anybody else is still listening and doesn't get that relationship, speak up and we can explain why that's the case. but I'll keep going otherwise. And so we know that, since we know that there's 15,000 bits per second per subcarrier, we know that our total bit rate is given to us as, where were we? 18 megabits per second, is that right? Yeah. So our total bit rate was 18 megabits per second. And so if each of our individual subcarriers handles 15,000 bits per second, or 15 kilobits per second, we can then just see that we have our total bit rate, 18 times 10 to the 6, divided by 15,000, will tell us how many subcarriers we have, because each subcarrier is responsible or can support 15,000 bits per second. If our channel can support 18 megabits per second, then this will tell us here how many subcarriers we need to achieve this full data rate. So doing the math, 18 times 10 to the 6 for 18 megabits per second divided by 15,000 tells us that we need 1,200 subcarriers, because each subcarrier does 15,000 bits per second. So with 12,000 subcarriers, we have a total bit rate of 18 megabits per second. Al's just got back and he's a little confused about this subcarrier relationship. Okay, so let's go back and take a look at why that's the case. So when we go back here, this is how we get the number of symbols per second. We know that each symbol lasts for this set amount of time, 66.67 times 10 to the negative 6 seconds. And so we can find the number of symbols in a second by dividing 1 full second by that time, and we'll find the number of individual symbols that fit in a second. And so that gives us our number of 15,000 symbols per second. Now we have to remember what a symbol actually is in the case of OFDM. Let me move down. And the thing is that, let me see what the easiest way to explain this is. I have to. No worries, Al. If you don't get it, that's why we're here. I don't want to answer questions with more questions, basically. But I want to make sure I can explain it properly as well. I don't want to just. So the important thing is that let me see. So on page 241, near the bottom of the page, the book basically says, and this is the important thing that we need to get, is that an OFDM symbol is different from what we're used to saying, like a QPSK symbol. And so basically, normally what we're used to a symbol being usually equals a representation of multiple bits being transmitted at once. And so that's when we're looking at QPSK, for example, and we have a symbol that indicates that we're sending multiple bits at once. Because remember, QPSK indicates 4 levels. And if we have 4 levels, that means we have 1, 2, 3, 4 basically indications. And so we're sending 4 bits at once with a QPSK system. That's not what a symbol means in OFDM. In OFDM, a symbol is basically equals group of samples from each subcarrier. Let me make sure that's clear. And so for OFDM, when we say that there's 15,000 symbols per second, each symbol is a sample from a subcarrier. And so if there's 15,000 symbols, that means there's 15,000 bits per second per subcarrier. Because each subcarrier has to be transmitting. One symbol means that we're sampling from multiple subcarriers at once. Let me just... And so the example the book says is if we were using, say we were using 16 QAM modulation, or I guess we could say QPSK is the example I like to use. If we were using QPSK modulation with OFDM, we could be one OFDM symbol could be 8 QPSK symbols at once. And so it basically what OFDM is saying is that you have different subcarriers and you're sampling each of them to make up the one OFDM symbol. So it's basically a package of all the individual subcarriers. It doesn't matter what those subcarriers are doing. Like we said, if the subcarriers are using QPSK and we're using an 8 block of OFDM, we would be sending 8 QPSK symbols. And that would be, our one OFDM symbol would be 8 QPSK symbols. And again, the explanation in the book, if my explanation of the book's explanation isn't doing it for you, page 242 in the book kind of goes into an explanation of why 241, 242 talks about this. But the essential thing is that we're saying we're doing 15,000 symbols per second, and each of those symbols, OFDM symbols, are samples of multiple subcarriers. And so if we're assuming that we're not doing any particular modulation of the subcarriers, each of the subcarriers has to have some data available each time we take a sample. And so if we're doing 15,000 symbols per second, each of our subcarriers has to be going at least the same rate, so that when we make the sample, there's actually information coming back. It's either a 0 or a 1. And so each of our subcarriers is 15,000 bits per second, because we're sampling a symbol each second of each of our subcarriers. So hopefully that makes a little bit more sense. And again, 241, 242 goes into some of the detail why an OFDM symbol is different from what we're used to saying with a QPSK symbol. But that's the main distinction to make there, and why we can make the assumption that we have 15,000 bits per second per subcarrier is because we're sampling 15,000 times a second. Each time we sample, our subcarrier has to have a bit of information for us. So they have to at least be going at 15,000 bits per second. Because an OFDM symbol is a sample of multiple subcarriers. And so each of our individual subcarriers has to be going at a bit rate that allows us to sample at our symbol rate. And so that tells us that our bit rate for our individual subcarriers has to at least be 15,000. It could be higher, but there's no indication that it's going to be higher. Because if it were higher, we could sample potentially a little bit faster. And so again, once we know that our subcarriers are 15,000 bits per second, we can find the number of subcarriers it would take to meet our total bit rate of 18 megabits per second, and that'll tell us how many subcarriers are in use. And that's what this problem is asking. And yeah, sorry, Stephen, I misunderstood what question you were talking about, but hopefully that explains it a little bit more. And that might be worth, if you're still confused about that, which I don't blame you if you are, it might be worth making a discussion post so Dr. Helm can share his perspective of it to see if he has a different way of describing it in a better way than I do. But now that we covered that question, I think it's about time to wrap up. As usual, if you have any other questions, you can shoot me an email. And again, I will be back next Thursday at the regular time, as usual. So next Thursday, next Sunday will be the next study sessions. But other than that, again, I mentioned this at the beginning, Al, you missed this. If you have questions on the midterm, so like if you had the right answer but you rounded differently or you typed in an answer in a way it didn't expect, Dr. Helm will be reviewing the midterms. He does do that. He goes over and makes sure there's not just basic like automatic grading errors, you know. And so if you have those questions, give it a few days to work itself out, and if there's still a mistake or something you disagree with, like midway through next week or the end of next week, either contact me about it or the grader or Dr. Helm. Probably me or the grader first, and then we'll escalate as needed. But we do our best to try to pick up like the automatic grading mistakes, but we don't always know unless somebody notifies us. So keep an eye on that. Just make sure everything went as you thought it would. And yeah, I will see everyone next week. Keep making your posts, keep doing everything, and we're on the downhill slope, I'd say. We're almost through with it, so keep up the hard work. All right. Thanks, everyone. See you next Thursday.